This invisible matter, which scientists call dark matter, represents perhaps the greatest puzzle in modern cosmology. It surrounds us, permeates the space between galaxies, and provides the gravitational scaffolding upon which all cosmic structure depends. Every breath you take occurs within a vast web of dark matter that extends from your immediate vicinity to the edges of the observable universe. Yet, despite decades of searching with the most sophisticated instruments ever built, we have never directly detected a single particle of this mysterious substance. The story of dark matter begins with a fundamental shock to human understanding, the realization that the universe we can see represents only a tiny fraction of what actually exists. When astronomers first began measuring the rotation of galaxies in the mid-20th century, they expected to find that stars at the edges of galaxies would orbit more slowly than those near the center, just as planets in our solar system orbit more slowly the farther they are from the Sun. Instead, they discovered something that seemed to violate the laws of physics. Stars at the edges of galaxies were moving so fast that they should have been flung out into space long ago. This discovery implied that galaxies contain far more mass than we can see in visible matter that provides the additional gravitational pull needed to keep fast-moving stars bound in their orbits. But this wasn't just a small correction to our understanding, it was a complete revolution. The amount of invisible matter required to explain galactic rotation turned out to be about 5 times greater than all the visible matter combined. Suddenly, everything we could see in the universe, stars, planets, gas clouds, even black holes, became a mere garnish on an invisible cosmic meal. The implications of this discovery cascade through every aspect of our understanding of the cosmos. Dark matter doesn't just influence individual galaxies, it shapes the large-scale structure of the entire universe. Computer simulations show that without dark matter, the universe would be a smooth, featureless expanse of gas, with no galaxies, no stars, and no planets. The invisible matter acts like a cosmic skeleton, providing the framework upon which all visible structure assembles. But dark matter's influence extends even deeper into cosmic history. In the earliest moments after the Big Bang, when the universe was a hot, dense soup of particles and radiation, dark matter began clumping together under its own gravity, while ordinary matter remained smooth and uniform. These early dark matter concentrations created the gravitational wells that eventually attracted ordinary matter, leading to the formation of the first stars and galaxies. Without dark matter's head start in the cosmic structure formation race, the universe might still be a dark, empty void. The search for dark matter has become one of the greatest detective stories in science, spanning underground laboratories deep beneath mountains, particle accelerators that recreate conditions from the early universe, and space telescopes that map the invisible matter's effects across cosmic scales. Scientists have proposed dozens of candidates for what dark matter might be: exotic particles, with names like WIMPs, axions, and sterile neutrinos, each requiring different experimental approaches and technological innovations to detect. What makes this mystery particularly profound is that it forces us to confront the limits of human perception and the assumptions we make about reality based on what our senses can detect. We live in a universe where the majority of matter is invisible to us, interacting with ordinary matter only through gravity. This invisible realm might operate according to principles we haven't discovered, contain forms of complexity we can't imagine, and play roles in cosmic evolution that we're only beginning to understand. The dark matter story also reveals the remarkable power of scientific reasoning to discover truths that transcend direct observation. Through careful measurements of galactic rotation, gravitational lensing effects, and the cosmic microwave background radiation, astronomers have mapped the distribution of invisible matter across the universe with extraordinary precision. We can see dark matter's fingerprints in the bending of light around galaxy clusters, detect its influence in the formation of cosmic structure, and measure its effects in the earliest observable moments of cosmic history. Yet, for all our sophisticated detection methods, dark matter remains tantalizingly elusive. Decades of experiments designed to catch dark matter particles interacting with ordinary matter have yielded only null results, forcing scientists to build ever more sensitive detectors and explore increasingly exotic theoretical possibilities. Each negative result teaches us something about what dark matter isn't: gradually narrowing the possibilities while the mystery deepens. This ongoing search for dark matter represents more than just an academic exercise. It touches on fundamental questions about the nature of reality itself. If we live in a universe dominated by invisible matter, what does this say about our cosmic significance? How does it change our understanding of our place in the cosmos to know that we're made of a rare and unusual form of matter that represents only a small fraction of what exists? The dark matter mystery also bridges multiple scientific disciplines in unprecedented ways. Particle physicists study dark matter to understand the fundamental building blocks of reality. Cosmologists investigate its role in cosmic evolution and structure formation. Astrophysicists examine its effects on star formation and galactic dynamics. Computer scientists develop algorithms to simulate dark matter's behavior across cosmic time. This interdisciplinary collaboration has led to new insights about the connections between the smallest and largest scales in nature. As we prepare to explore this invisible realm together, we'll journey through the history of dark matter's discovery, examine the evidence that convinced scientists of its existence, and explore the cutting-edge experiments designed to finally detect it directly. We'll consider alternative explanations that challenge the dark matter hypothesis and investigate what dark matter's existence might mean for our understanding of the cosmos and our place within it. Tonight's exploration will take us from the rotation curves of nearby galaxies to the cosmic web of structure that spans billions of light-years, from underground laboratories shielded from cosmic radiation to particle accelerators, probing the fundamental nature of matter itself. We'll discover how dark matter shaped the cosmic dark ages before the first stars ignited, how it continues to influence the formation of galaxies today, and how it might determine the ultimate fate of the universe. The story of dark matter is still being written, with new discoveries and technological advances constantly reshaping our understanding of this invisible realm. Whether dark matter consists of exotic particles waiting to be discovered, modifications to our understanding of gravity itself, or something even stranger than we can currently imagine, its study promises to reveal fundamental truths about the nature of reality. Let the gentle currents of cosmic mystery carry you forward as we begin our journey into the invisible skeleton that shapes everything we see. In the early 1970s, a pioneering astronomer named Vera Rubin was conducting what seemed like routine observations of nearby spiral galaxies at the Kitts Peak National Observatory in Arizona. Working with her colleague Kent Ford and his revolutionary spectrograph, an instrument capable of measuring the velocities of stars and gas clouds with unprecedented precision, Rubin was mapping how fast different parts of galaxies rotate around their centers. What she discovered would fundamentally challenge our understanding of the cosmos and reveal that the universe is far stranger than anyone had imagined. Rubin's work built upon decades of theoretical predictions about how galaxies should behave. Just as planets in our solar system follow Kepler's laws, with more distant planets orbiting more slowly than those closer to the Sun, astronomers expected that stars in the outer regions of galaxies would orbit more slowly than those near the galactic center. This expectation was based on the simple logic that most of a galaxy's mass should be concentrated in its bright central bulge, where millions of stars cluster together. Stars at the galaxy's edge, far from this central mass concentration, should feel weaker gravitational pull and therefore orbit more slowly. The mathematics behind this expectation was straightforward and well established. Newton's law of universal gravitation predicts that orbital velocity should decrease with distance from the center of mass, following what astronomers call a Keplerian decline. For a galaxy like the Milky Way, stars at the edge should be moving at roughly half the speed of stars near the center. This wasn't just theoretical speculation, it was a fundamental prediction of gravitational theory that had been confirmed countless times in our solar system and binary star systems. But when Rubin analyzed the spectra of light from stars and hydrogen gas in the Andromeda galaxy and dozens of other nearby spirals, she found something completely unexpected. Instead of the predicted decline in orbital velocities, she observed that stars at the edges of galaxies were moving just as fast as those near the center. The rotation curves graphs showing orbital velocity versus distance from the galactic center remained flat far beyond the visible edge of the galaxy's stellar disk. This observation was so contrary to theoretical expectations that Rubin initially questioned her measurements. She and Ford spent months checking and rechecking their data, looking for instrumental errors or systematic biases that might explain the discrepancy. They observed galaxy after galaxy, using different telescopes and different techniques, but the result remained consistent. Spiral galaxies were rotating in a way that seemed to violate the laws of physics. The implications of flat rotation curves were staggering. For stars at the edge of a galaxy to maintain such high orbital velocities, there had to be far more mass in the galaxy than could be accounted for by visible stars and gas. When Rubin calculated how much additional mass would be required to explain the observations, she found that galaxies must contain about 5 times more matter than what could be seen. This invisible matter had to be distributed throughout the galaxy's halo, extending far beyond the visible stars. Rubin's discovery met with significant skepticism from the astronomical community. Many colleagues suggested alternative explanations. Perhaps the gas clouds she was observing were not in stable orbits, but were being blown outward by stellar winds. Or maybe there were systematic errors in measuring distances to galaxies that threw off the velocity calculations. Some proposed that the outer regions of galaxies contained large numbers of faint stars or stellar remnants that had simply escaped detection. The resistance Rubin faced was compounded by the challenges she encountered as a woman in astronomy during an era when few women were accepted in observational astronomy. She had been denied access to the Palomar Observatory in the 1960s simply because she was female, and she often had to fight for telescope time and recognition of her work. Despite these obstacles, Rubin persisted with her observations, accumulating an ever-growing body of evidence that galaxies contained vast amounts of invisible matter. As more astronomers began confirming Rubin's observations with independent measurements, the reality of flat rotation curves became impossible to deny. Observations using radio telescopes to map hydrogen gas in the outer parts of galaxies showed the same pattern. Studies of satellite galaxies orbiting larger galaxies revealed that these satellites were moving too fast to be bound by the gravity of visible matter alone. The evidence for invisible matter in galaxies became overwhelming. The term dark matter began to gain currency in the astronomical literature, though it had been coined decades earlier by Fritz Zwicky in a different context. This invisible matter had to have unusual properties. It clearly interacted gravitationally with ordinary matter, but it didn't emit or absorb light like normal matter. It seemed to permeate the space around and within galaxies, without clustering into stars or other luminous objects. Rubin's work revealed that dark matter wasn't just a minor correction to our understanding of galactic structure, it was the dominant component of galaxies. The visible stars, that had been the focus of astronomical attention for centuries, turned out to be just trace contaminants floating within vast halos of invisible matter. Every galaxy was embedded in a dark matter halo that extended far beyond its visible boundaries and contained most of its mass. The flat rotation curve discovery also provided crucial insights into galaxy formation and evolution. Computer simulations showed that dark matter halos formed first in the early universe, creating gravitational wells that attracted ordinary matter and enabled the formation of galaxies. The properties of dark matter halos influenced how galaxies acquired their gas, formed their stars, and evolved over cosmic time. Understanding dark matter became essential to understanding how the universe developed its current structure. Kent Ford's spectrograph technology played a crucial role in making these discoveries possible. His instrument could measure velocities with a precision of just a few kilometers per second, revealing subtle features in galaxy rotation that previous instruments had missed. This technological advance, combined with Rubin's careful observational approach and willingness to challenge conventional wisdom, opened up an entirely new window on the universe. Rubin continued studying galaxy rotation throughout her career, extending her observations to different types of galaxies and refining our understanding of dark matter's distribution. Her work established the foundation for modern dark matter research and earned her recognition as one of the most important astronomers of the 20th century. Although she never received a Nobel Prize, a mission many consider a grave oversight, her discoveries fundamentally changed how we understand the cosmos. As we contemplate Rubin's revolutionary discovery, we begin to appreciate how a single astronomer's careful observations could reveal that the universe is dominated by invisible matter setting the stage for decades of investigation into the nature of this cosmic dark sector. 4 decades before Vera Rubin's galaxy rotation discoveries, an eccentric Swiss-American astronomer named Fritz Zwicky was making observations that would prove to be even more prescient. Working at the California Institute of Technology in the 1930s, Zwicky turned his attention to the Coma Cluster, a vast collection of over 1,000 galaxies located about 320 million light-years from Earth. What he found there would introduce the first evidence for dark matter and coin the very term that we still use today, though his discovery would be largely ignored for decades. Zwicky was studying the motions of individual galaxies within the Coma Cluster, measuring how fast they were moving relative to the cluster's center. Using the 18-inch Schmidt telescope at Mount Wilson Observatory, he painstakingly measured the redshifts of cluster galaxies, the stretching of their light toward longer wavelengths caused by their motion away from us. From these measurements, he could calculate the velocities of galaxies orbiting within the cluster's gravitational field. The theoretical framework for understanding galaxy clusters was based on the virial theorem, a fundamental principle of mechanics that relates the kinetic energy of orbiting objects to the gravitational potential energy of the system. For a gravitationally bound cluster of galaxies, the virial theorem predicts a specific relationship between the orbital velocities of the galaxies and the total mass of the cluster. Faster-moving galaxies require more mass to keep them gravitationally bound. Otherwise, they would escape into intergalactic space. When Zwicky applied the virial theorem to his observations of the Coma Cluster, he encountered a shocking discrepancy. The galaxies were moving far too fast, with velocities exceeding 1,000 kilometers per second to be held together by the gravitational attraction of the visible matter in the cluster. If the cluster contained only the mass that could be seen in the form of stars and galaxies, the high-velocity galaxies should have escaped long ago, dispersing the cluster into the surrounding cosmic void. Zwicky calculated that the Coma Cluster needed to be about 400 times more massive than what could be accounted for by its visible galaxies. This was an enormous discrepancy that couldn't be explained by small errors in measurement or minor corrections to theory. The cluster had to contain vast amounts of matter that produced gravitational effects but emitted no detectable light. Zwicky dubbed this invisible matter Dunkel Materie, dark matter, in his 1933 paper, introducing a term that would eventually become central to cosmology. The implications of Zwicky's discovery were so radical that most astronomers simply ignored them. The idea that the universe might be dominated by invisible matter seemed too extraordinary to take seriously. Many assumed that Zwicky had made an error in his calculations, or that there was some unknown systematic effect contaminating his observations. The astronomical community of the 1930s was not prepared to accept that their understanding of cosmic matter was fundamentally incomplete. Zwicky himself was a brilliant but difficult personality who often clashed with his colleagues and made outrageous claims that damaged his credibility. He was known for his harsh criticism of other astronomers and his tendency to pursue unconventional ideas that seemed to contradict established wisdom. This reputation made it easier for the astronomical community to dismiss his dark matter discovery as another example of Zwicky's eccentricity rather than a genuine scientific breakthrough. The technological limitations of 1930s astronomy also made it difficult to follow up on Zwicky's observations. Measuring galaxy velocities required long exposures with photographic plates and careful analysis of spectral lines, a time-consuming process that few observatories were equipped to perform efficiently. The uncertainty in individual velocity measurements was large enough that some astronomers questioned whether the apparent discrepancy was real or just the result of observational errors. Alternative explanations for the missing mass problem were proposed throughout the following decades. Some astronomers suggested that galaxy clusters might contain large amounts of hot gas between the galaxies that had escaped detection. Others proposed that clusters might be populated by numerous faint galaxies or stellar remnants that were too dim to observe with existing telescopes. Still others argued that the clusters might not be gravitationally bound systems at all, but chance alignments of galaxies along our line of sight. The development of modified Newtonian dynamics, MOND, in the 1980s provided another potential resolution to Zwicky's missing mass problem. MOND proposed by Israeli physicist Mordechai Milgram, suggested that Newton's laws of gravity might break down at the extremely low accelerations present in galaxy clusters and galactic outskirts. If gravity were stronger than Newton predicted at large distances, it might be possible to explain cluster dynamics without invoking dark matter. However, observations in the 1970s and 1980s began to vindicate Zwicky's original insights. X-ray observations revealed vast amounts of hot gas within galaxy clusters, gas that contributed to the cluster's mass, but still fell far short of explaining the missing mass problem. The total mass of hot gas, combined with the visible galaxies, still accounted for only about 15% of the mass required to explain cluster dynamics. Dark matter remained the dominant component. Gravitational lensing observations provided even more compelling evidence for dark matter in galaxy clusters. When light from distant galaxies passes through a massive cluster, the cluster's gravity bends the light path, creating distorted and magnified images of the background galaxies. The amount of lensing depends directly on the cluster's total mass, providing an independent way to measure cluster masses that doesn't rely on galaxy velocities or any assumptions about equilibrium. Lensing measurements consistently confirmed that galaxy clusters contain about 6 times more mass than can be accounted for by visible matter and hot gas combined. This invisible mass is distributed in roughly spherical halos around clusters, with the densest concentrations near the cluster centers. The lensing evidence for dark matter was particularly compelling because it didn't depend on assumptions about cluster dynamics or the gravitational theory being used. Modern observations have refined Zwicky's original estimates while confirming his basic conclusion. Today's measurements show that galaxy clusters typically contain about 85% dark matter, 12% hot gas, and only 3% stars and galaxies. This composition has remained remarkably consistent across different clusters and cosmic epochs, suggesting that dark matter plays a fundamental role in cluster formation and evolution. Computer simulations of cosmic structure formation have revealed how galaxy clusters assemble through the merger of smaller dark matter halos over billions of years. These simulations show that clusters form at the intersections of vast, dark matter filaments that span the observable universe. The visible galaxies represent just the tip of the iceberg, the small fraction of matter that has cooled and condensed into stars within much larger dark matter structures. As we reflect on Zwicky's pioneering observations and the decades of confirmation that followed, we see how one astronomer's careful application of fundamental physics principles revealed the first evidence that our universe is dominated by invisible matter. In one of the most elegant demonstrations of Einstein's general relativity, the universe itself has provided us with a tool to map its invisible components. Gravitational lensing, the bending of light by massive objects, offers a direct way to observe dark matter's gravitational effects without relying on assumptions about how galaxies and stars move within dark matter halos. This cosmic magnifying glass has revealed the distribution of dark matter across the universe with stunning clarity, providing some of the most compelling evidence that invisible matter dominates cosmic structure. Einstein's general theory of relativity, published in 1915, predicted that massive objects would curve the fabric of space-time, causing light rays to follow bent paths when passing near them. Einstein himself calculated that light from distant stars would be deflected when passing close to the Sun, and this prediction was famously confirmed during the solar eclipse of 1919. But Einstein thought that gravitational lensing by more distant objects would be too weak to observe, dismissing it as having no great practical importance. The first discovery of gravitational lensing by a galaxy occurred in 1979, when astronomers found what appeared to be 2 identical quasars separated by just a few arc-seconds on the sky. Further investigation revealed that these were actually 2 images of the same quasar, created when its light was bent around an intervening galaxy. This twin quasar provided the first confirmation that galaxies could act as gravitational lenses, opening up an entirely new field of astronomical observation. Gravitational lensing works because any mass, visible or invisible curves, spacetime, and light, follows the curved paths through that spacetime. When light from a distant galaxy passes through or near a massive foreground object like a galaxy cluster, the gravitational field acts like a giant lens, bending the light rays and creating distorted, magnified images of the background galaxy. The amount of distortion depends directly on the total mass of the lensing object, making gravitational lensing a powerful tool for weighing cosmic structures. Strong gravitational lensing creates the most spectacular and easily observed effects. When a massive galaxy cluster lies almost perfectly aligned with a distant galaxy, it can create multiple images of the background galaxy arranged in arcs or even complete rings around the cluster. These Einstein rings provide direct visual evidence of space-time curvature and allow astronomers to measure the cluster's mass with remarkable precision. The most massive clusters can magnify background galaxies by factors of 10 or more, revealing distant objects that would otherwise be too faint to observe. Weak gravitational lensing offers an even more powerful tool for mapping dark matter, though its effects are much more subtle. Instead of creating obvious multiple images or dramatic arcs, weak lensing causes tiny distortions in the shapes of background galaxies. Distortions so small that they can only be detected statistically by analyzing the shapes of thousands of galaxies. By measuring how background galaxies are systematically stretched and aligned, astronomers can reconstruct the distribution of dark matter in the foreground with exquisite detail. The Hubble Space Telescope has been instrumental in advancing gravitational lensing studies, providing the sharp images necessary to detect weak lensing effects and the sensitivity needed to observe faint, lensed galaxies. Hubble's observations of galaxy clusters have created detailed maps of dark matter distribution, revealing how dark matter clumps and flows on scales ranging from individual galaxies to massive cluster systems. These maps show dark matter forming a cosmic web of filaments and nodes that serves as the scaffolding for all visible structure. One of the most dramatic confirmations of dark matter's existence came from observations of the Bullet Cluster, a system where two galaxy clusters have collided and passed through each other. In this cosmic collision, the hot gas between galaxies has been slowed down by electromagnetic interactions and shock heating, causing it to lag behind the galaxies themselves. But dark matter, which interacts only gravitationally, has passed right through the collision, largely undisturbed. Gravitational lensing maps of the Bullet Cluster show that most of the mass, and therefore most of the gravitational lensing, is associated with the galaxies that have passed through the collision, not with the hot gas that has been left behind. This spatial separation of normal matter and gravitational mass provides smoking gun evidence that dark matter exists as a separate component that doesn't interact electromagnetically with normal matter. No modification of gravity can easily explain why gravitational effects would be spatially separated from all forms of normal matter. Weak lensing surveys have extended these measurements to vast areas of sky, creating three-dimensional maps of dark matter distribution across billions of light years. Projects like the Dark Energy Survey, the Kilodegree Survey, and the upcoming Euclid mission are measuring the shapes of hundreds of millions of galaxies to trace dark matter structure throughout cosmic history. These surveys reveal how dark matter has evolved over time, providing crucial tests of our understanding of cosmic structure formation. The cosmic shear signal, the correlated distortion of galaxy shapes caused by intervening dark matter, has become one of the most important tools in modern cosmology. By measuring how the strength of cosmic shear changes with distance and angular scale, astronomers can determine fundamental cosmological parameters like the total amount of dark matter, the rate of cosmic expansion, and the amplitude of matter fluctuations in the early universe. Gravitational lensing has also revealed that dark matter halos extend far beyond the visible boundaries of galaxies. Weak lensing measurements show that individual galaxies are surrounded by dark matter halos that can extend for hundreds of thousands of light years, much larger than the stellar disks that define the visible size of galaxies. These extended halos contain most of the galaxy's mass and play crucial roles in determining how galaxies acquire gas, form stars, and interact with their neighbors. Recent advances in machine learning and artificial intelligence have revolutionized how astronomers analyze gravitational lensing data. Neural networks can now identify lensed galaxies automatically, measure subtle shape distortions with superhuman precision, and reconstruct dark matter maps from noisy observational data. These computational advances are enabling lensing studies with unprecedented statistical power and opening up new possibilities for probing dark matter's properties. Future space-based missions like the Nancy Grace Roman Space Telescope and the Euclid satellite will extend weak lensing measurements to even larger scales and higher redshifts, providing detailed maps of how dark matter structure has evolved over most of cosmic history. These observations will test our understanding of dark matter's role in cosmic evolution and potentially reveal new physics beyond the standard cosmological model. As we contemplate these cosmic lenses that make the invisible visible, we gain deep appreciation for how the universe has provided us with tools to study its own hidden components. Through the elegant physics of curved space-time, we can map the distribution of matter that emits no light yet shapes everything we see. In the faint afterglow of the Big Bang that still fills the universe today, astronomers have found some of the most precise evidence for dark matter's existence and discovered exactly how much dark matter the universe contains. The cosmic microwave background radiation, the oldest light in the universe, carries within its subtle temperature patterns a detailed record of how dark matter influenced cosmic evolution during the universe's first few 100,000 years. This ancient light has revealed that dark matter makes up precisely 26.8% of the universe's total energy density, while ordinary matter accounts for only 4.9%. The cosmic microwave background originates from the epoch of recombination, about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was filled with hot plasma that scattered photons continuously, making it opaque to light. When recombination occurred, photons were suddenly free to travel through space without being scattered, creating the first transparent moment in cosmic history. The temperature patterns we observe in the cosmic microwave background reflect density fluctuations that existed in the early universe regions that were slightly denser or less dense than average. These fluctuations originated as quantum mechanical uncertainties during cosmic inflation, but their evolution during the first 380,000 years was profoundly influenced by the presence of dark matter. Understanding these patterns requires carefully modeling how both dark matter and ordinary matter behaved during the universe's infancy. In the early universe, ordinary matter was coupled to radiation through electromagnetic interactions, preventing it from clumping together under gravity while the universe remained hot and ionized. Photons continually scattered off free electrons, creating radiation pressure that resisted gravitational collapse. This coupling between matter and radiation created acoustic oscillations, sound waves that propagated through the cosmic plasma at about half the speed of light, causing density fluctuations to oscillate in a regular pattern. Dark matter, however, was not coupled to radiation because it doesn't interact electromagnetically. This meant that dark matter could begin clumping together under its own gravity immediately after inflation, creating the seeds of cosmic structure formation. While ordinary matter was prevented from forming significant density concentrations by radiation pressure, dark matter was free to collapse into the gravitational potential wells that would eventually become galaxies and galaxy clusters. The interplay between dark matter and ordinary matter during this epoch created a characteristic signature in the cosmic microwave background. The acoustic oscillations in the ordinary matter radiation fluid were modulated by the gravitational effects of the underlying dark matter distribution. Regions where dark matter had begun to concentrate provided extra gravitational pull that enhanced the amplitude of acoustic oscillations, while regions with less dark matter showed weaker oscillations. When cosmologists analyze the angular power spectrum of cosmic microwave background temperature fluctuations, they see a series of acoustic peaks that encode information about the universe's composition and geometry. The relative heights, positions, and widths of these peaks depend sensitively on how much dark matter, ordinary matter, and dark energy the universe contains. By fitting theoretical models to the observed peak structure, astronomers can determine these cosmic ingredients with remarkable precision. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, and the Planck satellite, which operated from 2009 to 2013, have provided increasingly precise measurements of the cosmic microwave background. These observations have determined that the universe consists of 68.3% dark energy, 26.8% dark matter, and 4.9% ordinary matter, with uncertainties of less than 1%. This represents one of the most precise measurements of cosmic composition ever achieved. The cosmic microwave background also reveals the crucial role that dark matter played in enabling structure formation. Computer simulations show that in a universe without dark matter, the acoustic oscillations would have erased all density fluctuations on scales smaller than galaxy clusters. The universe would have remained smooth and featureless, with no galaxies, no stars, and no planets. Dark matter provided the gravitational seeds that allowed structure to form despite the smoothing effects of radiation pressure. The baryon acoustic oscillation scale, the characteristic distance that sound waves could travel in the early universe, has become a standard ruler for measuring cosmic distances and the expansion history of the universe. The fact that we can measure this scale both in the cosmic microwave background and in the large-scale distribution of galaxies today provides powerful confirmation that our understanding of early universe physics is correct, and that dark matter played the role that cosmologists have attributed to it. Polarization measurements of the cosmic microwave background provide additional information about the early universe and dark matter's properties. The polarization patterns encode information about how photons were scattered during the epoch of recombination and can reveal details about the ionization history of the universe. Future measurements of polarization could potentially detect gravitational waves from cosmic inflation, providing insights into the energy scales at which dark matter particles might have been produced. The cosmic microwave background also constrains the properties that dark matter particles can have. If dark matter particles had significant electromagnetic interactions, they would have affected the recombination process and altered the observed temperature and polarization patterns. The absence of such signatures places strict limits on how strongly dark matter can interact with photons and ordinary matter. Similarly, if dark matter particles were very light or had significant kinetic energy during recombination, they would have erased small-scale structure in ways that would be visible in the cosmic microwave background. The observed pattern of fluctuations requires that dark matter particles be relatively massive and slow-moving, consistent with the cold, dark matter that forms the foundation of modern cosmological models. Recent analyses of cosmic microwave background data have also searched for signatures of dark matter annihilation or decay during the early universe. If dark matter particles occasionally destroyed each other or spontaneously decayed into other particles, the resulting energy injection could have altered the ionization state of the early universe in detectable ways. Current observations place strict limits on such processes, constraining theories about dark matter's particle physics properties. The precision of cosmic microwave background measurements has made cosmology a high-precision science, allowing astronomers to test theoretical models with unprecedented accuracy. The consistency between cosmic microwave background observations and other cosmological probes, including Type Ia supernovae, baryon acoustic oscillations, and gravitational lensing, provides strong confirmation that our dark matter-dominated cosmological model is fundamentally correct. As we contemplate this ancient light that has traveled 13.8 billion years to reach us, we gain deep appreciation for how the earliest moments of cosmic history were shaped by the invisible matter that continues to dominate the universe today. In vast computer simulations that model the evolution of billions of dark matter particles across cosmic time, scientists have discovered how the invisible skeleton of the universe grows from tiny quantum fluctuations into the magnificent cosmic web of structure we observe today. These computational experiments, among the most complex calculations ever performed, have revealed that dark matter doesn't distribute itself uniformly through space, but instead forms an intricate network of filaments, walls, and dense nodes that serves as the scaffolding upon which all visible matter assembles. The Millennium simulation, completed in 2005, marked a watershed moment in computational cosmology. This massive calculation followed the gravitational evolution of more than 10 billion dark matter particles from shortly after the Big Bang until the present day, creating a detailed model of how cosmic structure formed over 13.8 billion years. The simulation required months of computing time on supercomputers and generated datasets containing petabytes of information about dark matter's distribution and evolution. When astronomers analyzed the results of the Millennium simulation and its successors, they discovered that dark matter naturally organizes itself into a cosmic web structure that bears striking resemblance to biological systems like neural networks or the circulatory system. About half of all dark matter lies in dense filaments that connect massive nodes where galaxy clusters form. These filaments can stretch for hundreds of millions of light years, creating a vast network that permeates the observable universe. The remaining dark matter is distributed between sheets or walls that surround enormous voids, regions of space with very little matter. These voids can be hundreds of millions of light years across, containing less than 10% of the average cosmic density. The contrast between the dense filaments and empty voids creates a foam-like structure that emerged naturally from the gravitational amplification of tiny fluctuations present in the early universe. Dark matter halos represent the fundamental building blocks of cosmic structure in these simulations. Halos form when dark matter particles collapse under their own gravity, creating bound structures with characteristic density profiles. The smallest halos might contain only as much mass as a small asteroid, while the largest can contain as much mass as 1,000 galaxies. These halos span an enormous range of masses, following a nearly universal distribution across all scales. The hierarchical nature of structure formation emerges clearly from the simulations. Small dark matter halos form first, then merge and accrete to form larger halos in a bottom-up process that continues throughout cosmic history. This hierarchy explains why galaxies are often found in groups and clusters. They form within dark matter halos that are themselves part of larger halo systems. The Milky Way, for example, sits within a dark matter halo that is part of the local group, which is itself falling toward the much larger Virgo cluster. Galaxy formation within dark matter halos represents one of the most complex aspects of these simulations. While dark matter provides the gravitational framework, the formation of actual galaxies requires modeling how ordinary matter cools, flows into halos, forms stars, and gets dispersed by stellar feedback processes. These hydrodynamic simulations must account for gas physics, star formation, supernova explosions, and black hole feedback processes that operate on vastly different scales from the dark matter dynamics. The Illustris, Eagle, and other state-of-the-art simulations have successfully reproduced many observed properties of galaxies by including detailed models of these baryonic processes. They show how galaxies acquire their gas supply through smooth accretion along dark matter filaments, how star formation occurs in bursts triggered by galaxy mergers, and how feedback from stars and black holes can regulate or even halt star formation. These simulations reveal that galaxy properties are intimately connected to the properties of their dark matter halos. One of the most important predictions of dark matter simulations is the relationship between halo mass and galaxy properties. More massive dark matter halos tend to host more luminous galaxies with more stars, but this relationship is not simple. The efficiency of star formation depends on halo mass in complex ways, with the most efficient star formation occurring in halos with masses similar to the Milky Way's halo. Very massive halos form elliptical galaxies where star formation has been largely shut off, while very small halos may contain only a few stars or no visible galaxy at all. The simulations also predict the existence of numerous satellite galaxies orbiting within larger dark matter halos. The Milky Way's halo, for example, should contain hundreds of smaller subhalos that could potentially host dwarf satellite galaxies. Observations have confirmed the existence of dozens of such satellites around the Milky Way, though fewer than the simulations predict a discrepancy known as the missing satellites problem that remains an active area of research. Dark matter's role in galaxy evolution extends throughout cosmic history. In the early universe, when galaxies were first forming, dark matter halos were still growing rapidly through mergers and accretion. This violent environment triggered intense bursts of star formation and fed the supermassive black holes that we observe in galaxy centers. As the universe aged and dark matter halos became more mature, galaxy formation became a more gentle process, dominated by steady gas accretion rather than dramatic mergers. The cosmic web structure predicted by dark matter simulations has been confirmed through observations of galaxy distributions and intergalactic gas. Galaxy surveys like the Sloan Digital Sky Survey have mapped the three-dimensional positions of millions of galaxies, revealing the same filamentary structure seen in dark matter simulations. Observations of the Lyman alpha forest absorption lines in quasar spectra, caused by intergalactic hydrogen, show that gas traces the dark matter filaments predicted by the simulations. Machine learning and artificial intelligence techniques are revolutionizing how astronomers analyze these massive simulation datasets. Neural networks can automatically identify dark matter halos, track their merger histories, and predict which halos will host galaxies. These tools are enabling new discoveries about how galaxy properties depend on their cosmic environment and evolutionary history. Future simulations will model even larger volumes of the universe with higher resolution, potentially tracking individual star formation events within the cosmic web framework. The next generation of supercomputers will enable simulations that follow dark matter dynamics, gas physics, star formation, and black hole growth self-consistently across cosmic time. These simulations will test our understanding of dark matter's role in cosmic evolution and predict what future telescopes should observe. As we contemplate these digital universes that capture the gravitational dance of trillions of dark matter particles across billions of years, we gain profound appreciation for how invisible matter has woven the cosmic web that connects everything in the universe. In the first few minutes after the Big Bang, when the universe was hot enough for nuclear reactions to occur, the cosmos became a vast nuclear reactor that forged the lightest elements from the primordial soup of protons and neutrons. This epoch of Big Bang nucleosynthesis has provided one of the most precise measurements of how much ordinary matter exists in the universe, and revealed that ordinary matter accounts for less than 5% of the cosmic inventory. This ancient nuclear archaeology has proven that dark matter cannot be made of ordinary atoms and must consist of something fundamentally different from all the matter we see around us. Big Bang nucleosynthesis occurred during a brief window in cosmic history, beginning about 1 second after the Big Bang, when the universe had cooled enough for protons and neutrons to exist in stable form, and ending about 20 minutes later, when the universe became too cool and dilute for nuclear reactions to continue. During this cosmic moment, the universe was a hot, dense nuclear plasma with temperatures reaching billions of degrees, conditions similar to the cores of the most massive stars, but extending throughout all of space. The nuclear physics of this epoch is well understood because it involves the same fundamental processes that power stars and nuclear reactors. As the universe expanded and cooled, protons and neutrons began combining to form deuterium-heavy hydrogen with one proton and one neutron. The formation of deuterium was crucial because it served as a stepping stone to heavier elements. Deuterium nuclei could fuse with additional protons or neutrons to form tritium and helium-3, which could then combine to produce helium-4, the most abundant product of Big Bang nucleosynthesis. The key insight of Big Bang nucleosynthesis theory is that the abundances of light elements produced during this epoch depend sensitively on the density of ordinary matter in the universe. If there had been more protons and neutrons available, the nuclear reactions would have proceeded more efficiently, producing more helium and burning more of the primordial hydrogen. If there had been fewer nucleons, less helium would have formed and more hydrogen would have survived unchanged. Observations of the oldest stars and gas clouds in the universe reveal the primordial abundances of light elements, providing a fossil record of Big Bang nucleosynthesis. These measurements show that about 75% of ordinary matter emerged from the Big Bang as hydrogen, 25% as helium-4, and tiny traces as deuterium, helium-3, and lithium-7. The precise ratios of these elements can be used to calculate backwards to determine how much ordinary matter the universe contained during nucleosynthesis. When cosmologists perform this calculation, they find that ordinary matter, the stuff that makes up atoms, molecules, stars, and planets, accounts for only about 4.9% of the universe's total energy density. This measurement is remarkably precise, with uncertainties of less than 0.1%, and it has been confirmed by independent observations of the cosmic microwave background radiation. The consistency between these two completely different probes provides strong confirmation that our understanding of the early universe is fundamentally correct. This precise measurement of ordinary matter abundance immediately rules out many potential explanations for dark matter. Dark matter cannot consist of ordinary atoms that have simply escaped detection, because Big Bang nucleosynthesis tells us exactly how many ordinary atoms were produced in the early universe. Even if these atoms were locked up in brown dwarfs, black holes, or other dark objects, they would still count toward the ordinary matter budget and could not account for the additional matter needed to explain galactic rotation curves and cluster dynamics. The deuterium abundance provides a particularly precise barometer of ordinary matter density because deuterium is easily destroyed in stellar nuclear reactions. Unlike helium, which is also produced in stars, deuterium can only be destroyed, never created, in post-Big Bang astrophysical processes. This means that the deuterium we observe today represents a lower limit on the amount produced during Big Bang nucleosynthesis, providing a clean measurement of primordial conditions. Observations of deuterium in high redshift quasar absorption systems, gas clouds that existed when the universe was much younger, have revealed primordial deuterium abundances with remarkable precision. These measurements show that deuterium makes up about 25 parts per million of ordinary matter by number, corresponding to a specific density of ordinary matter that matches the cosmic microwave background measurements almost exactly. The lithium problem represents one of the few discrepancies in Big Bang nucleosynthesis theory. Observations show that the oldest stars contain about 3 times less lithium-7 than Big Bang nucleosynthesis predicts. This discrepancy might indicate new physics during the nucleosynthesis epoch, stellar processes that have destroyed primordial lithium, or systematic errors in the observations. Despite decades of investigation, the lithium problem remains unsolved, though it doesn't affect the conclusions about overall ordinary matter abundance. Big Bang nucleosynthesis also places constraints on exotic forms of ordinary matter that might have been proposed as dark matter candidates. For example, if dark matter consisted of primordial black holes formed from ordinary matter, their formation would have altered the expansion rate during nucleosynthesis and changed the predicted element abundances. The observed abundances place strict limits on how much ordinary matter could have been converted into black holes during the early universe. The success of Big Bang nucleosynthesis theory represents one of the great triumphs of modern cosmology. The theory was developed in the 1940s by George Gamow, Ralph Alpher, and Robert Herman, decades before the cosmic microwave background was discovered and when our understanding of nuclear physics was much more primitive. Yet their basic framework has withstood every observational test and continues to provide precise predictions about cosmic composition. Recent advances in nuclear physics have refined the calculations of Big Bang nucleosynthesis by including previously neglected nuclear reactions and improving the fundamental constants that govern nuclear interactions. These improvements have reduced the theoretical uncertainties in predicted element abundances, making Big Bang nucleosynthesis an even more precise probe of cosmic composition. The nucleosynthesis constraint on ordinary matter has also been crucial for understanding dark energy. Since ordinary matter and dark matter together account for only about 32% of the universe's energy density, the remaining 68% must be something else entirely, the mysterious dark energy that drives cosmic acceleration. Without the precise measurement of ordinary matter from Big Bang nucleosynthesis, astronomers could not have determined dark energy's contribution to cosmic dynamics. As we contemplate this ancient nuclear forge that operated throughout the universe for just a few minutes, yet determined the cosmic matter budget for all subsequent time, we gain deep appreciation for how the earliest moments of cosmic history continue to shape the universe we observe today. In the deepest underground laboratories on Earth, surrounded by miles of rock that shield delicate detectors from cosmic radiation, scientists are conducting one of the most challenging experiments ever attempted, trying to catch dark matter particles as they pass through ordinary matter. The leading candidates in this cosmic detective story are called WIMPs, weakly interacting massive particles, theoretical entities that could explain dark matter's gravitational effects while remaining essentially invisible to all the instruments we've built to study the universe. The WIMP hypothesis emerged from particle physics theories developed in the 1970s and 1980s. particularly supersymmetry, a theoretical framework that predicts the existence of partner particles for every known particle in the Standard Model. In supersymmetric theories, every ordinary particle has a sparticle counterpart with similar properties but different quantum spin. The lightest of these supersymmetric particles would be stable and could provide a natural dark matter candidate with just the right properties to explain cosmic observations. What makes WIMPs so appealing as dark matter candidates is an apparent cosmic coincidence known as the WIMP miracle. When particle physicists calculate how many WIMPs would have been produced in the early universe, they find that particles with weak nuclear force interaction, strengths, and masses similar to those predicted by supersymmetry would naturally have the right abundance to account for dark matter today. This remarkable coincidence suggests that dark matter might be intimately connected to the same physics that governs the fundamental particles and forces we can study in laboratory experiments. The story of how WIMPs could become dark matter begins in the hot, dense, early universe, when all particles existed in thermal equilibrium, constantly being created and destroyed through high-energy collisions. As the universe expanded and cooled, the creation of new WIMP particles eventually stopped, but the existing WIMPs continued to annihilate with each other until their density became so low that finding an annihilation partner became extremely rare. This freeze-out process left behind a relic abundance of WIMPs that depends only on their interaction strength and mass. Direct detection experiments attempt to observe WIMPs by detecting the tiny amount of energy they deposit when they occasionally collide with atomic nuclei in carefully prepared target materials. These collisions would be extraordinarily rare. A WIMP detector might register only a few events per year, even if it contains tons of target material. The energy deposited in each collision would be minuscule, equivalent to dropping a single grain of sand from a height of about 1 millimeter. The technical challenges of WIMP detection are staggering. Detectors must be sensitive enough to register energy deposits of just a few keV, about 1,000 times smaller than the energy of visible light photons. They must be shielded from cosmic rays, natural radioactivity, and even vibrations from human activity that could create false signals. The materials used in detector construction must be among the purest ever created, with radioactive contamination levels billions of times lower than ordinary commercial materials. Underground laboratories provide the essential shielding needed for WIMP searches. Facilities like the Sanford Underground Research Facility in South Dakota, the Gran Sasso National Laboratory in Italy, and Snow Lab in Canada are located thousands of feet underground, where the overlying rock absorbs cosmic rays that would otherwise overwhelm any dark matter signal. Even in these deep facilities, detectors must be surrounded by additional layers of shielding made from ultra-pure materials like copper and lead. Liquid xenon detectors have emerged as the leading technology for WIMP searches. The X-Xenon collaboration, the Lux Zeppelin experiment, and similar projects use tanks containing hundreds of kilograms of liquid xenon cooled to extremely low temperatures. When a WIMP or other particle collides with a xenon nucleus, it produces both light and electrical charge that can be detected with exquisite sensitivity. The ratio of light to charge signals helps distinguish WIMP interactions from background events caused by ordinary particles. Despite decades of increasingly sensitive searches, no WIMP detector has found convincing evidence for dark matter interactions. Each null result places stronger constraints on WIMP properties, gradually excluding regions of the theoretical parameter space where WIMPs could exist. The most sensitive experiments can now detect WIMP interactions that are more than 1 trillion times weaker than ordinary weak nuclear interactions, yet they continue to see only background events. The lack of WIMP detection has led to increasingly exotic theoretical proposals. Some models suggest that WIMPs might interact primarily with neutrons rather than protons, requiring detectors with different target materials. Others propose that WIMPs might have electromagnetic interactions so weak that they've escaped detection, or that they might interact through forces that don't exist in the standard model of particle physics. Alternative direct detection strategies are being explored as WIMP searches reach their sensitivity limits. Some experiments are looking for annual modulation signals, tiny variations in detection rates that should occur as Earth orbits through the galaxy's dark matter halo. The Dama collaboration has claimed to observe such an annual modulation for over 2 decades. but other experiments have failed to confirm this result using different detector technologies. Complementary searches for WIMPs are being conducted at particle accelerators like the Large Hadron Collider. If WIMPs can be produced in high-energy collisions between ordinary particles, they would escape the detectors without being directly observed, creating missing energy signatures that could be detected indirectly. So far, these accelerator searches have also failed to find evidence for WIMP production, though they provide important constraints on WIMP properties that complement the underground searches. The future of WIMP detection depends on building even more sensitive detectors with larger target masses and lower background rates. Next-generation experiments like Darwin and Argo will use tens of tons of liquid xenon to search for WIMPs with unprecedented sensitivity. These detectors will be so sensitive that they'll begin to see neutrinos from the sun, creating an irreducible background that represents the ultimate limit of WIMP detection technology. If these future experiments fail to detect WIMPs, it would force a fundamental reconsideration of dark matter's nature. The null results might indicate that dark matter doesn't consist of WIMPs at all, or that WIMP interactions are so weak that they'll never be detectable with foreseeable technology. This would redirect the search toward alternative dark matter candidates with very different properties and detection methods. As we contemplate these underground sentinels, waiting patiently for dark matter particles to reveal themselves, we appreciate the remarkable dedication of scientists who have spent careers searching for something that might interact with ordinary matter only once in a detector's entire operational lifetime. In the realm of theoretical particle physics, few discoveries would be more elegant than finding that dark matter consists of axions, hypothetical particles, so light and weakly interacting that they could fill the universe while remaining essentially invisible to ordinary matter. Named after a laundry detergent because they would clean up one of the most perplexing problems in quantum chromodynamics, axions represent a completely different approach to dark matter that requires revolutionary detection techniques involving powerful magnetic fields and microwave cavities. The axion emerged from attempts to solve the strong CP problem, one of the most puzzling mysteries in the standard model of particle physics. The equations governing the strong nuclear force, the force that binds quarks together inside protons and neutrons, contain a term that should cause neutrons to have a measurable electric dipole moment. However, the most sensitive experiments have shown that neutrons have no detectable electric dipole moment, indicating that this problematic term in the equations must be essentially zero. In 1977, Roberto Pecci and Helen Quinn proposed an elegant solution to this puzzle. Perhaps the problematic term in the strong force equations is actually a dynamical field that naturally relaxes to zero through a process similar to a ball rolling down a hill to its lowest energy state. This Pecci-Quinn field would have an associated particle, which Frank Wilczek later named the axion after the cleaning product, because it cleaned up the theoretical mess of the strong CP problem. If axions exist, they would have remarkable properties that make them excellent dark matter candidates. They would be extraordinarily light, potentially billions of times lighter than electrons, and would interact with ordinary matter so weakly that they could pass through the entire Earth without a single interaction. Yet despite their ghostly nature, axions could be produced copiously in the early universe through various mechanisms, potentially accounting for all of dark matter. The production of axion dark matter in the early universe differs fundamentally from the thermal freeze-out process that would create WIMP dark matter. Instead of being produced through particle collisions and then freezing out of thermal equilibrium, axions would be created through a process called vacuum realignment. During cosmic inflation, quantum fluctuations would set the axion field to random values throughout space. When the universe cooled below a critical temperature, these field values would begin oscillating around their minimum energy state, creating a sea of axion particles with extremely low velocities. This cold production mechanism means that axion dark matter would consist of particles moving much more slowly than WIMPs, so slowly that their velocities would be negligible compared to the speed of light. From a cosmological perspective, this makes axions behave like cold dark matter that can form the scaffolding for cosmic structure formation, but their individual particle properties would be completely different from the massive particles typically associated with cold dark matter scenarios. Detecting axions requires exploiting their predicted ability to convert into photons in the presence of strong magnetic fields. According to the theory, when axions pass through a powerful magnetic field, some of them should transform into microwave photons with frequencies that depend on the axion's mass. This conversion process is extraordinarily inefficient. Only about one axion in a trillion would convert to a photon, even in the strongest magnetic fields humans can create. The Axion Dark Matter E-experiment, ADMX, at the University of Washington, represents the most sensitive search for axion dark matter currently operating. ADMX uses a cylindrical microwave cavity placed inside a powerful superconducting magnet. If axions from the dark matter halo surrounding our galaxy enter the cavity, some should convert to microwave photons that resonate within the cavity, creating a faint signal that can be detected with ultra-sensitive amplifiers cooled to temperatures just above absolute zero. The technical challenges of axion detection rival those faced by WIMP experiments. The expected signal is so weak that it would be completely overwhelmed by thermal noise unless the detectors are cooled to millikelvin temperatures 1,000 times colder than the temperature of outer space. The resonant cavities must be precisely tuned to the frequency corresponding to the axion's mass. But since the axion mass is unknown, searchers must scan across a wide range of possible frequencies. Quantum mechanics places fundamental limits on the sensitivity of axion detectors through the quantum noise associated with electromagnetic field measurements. To overcome these limits, ADMX and other experiments are incorporating quantum-limited amplifiers and exploring quantum squeezing techniques that could enhance detection sensitivity. These technologies represent some of the most advanced applications of quantum mechanics to experimental physics. The search for axions extends beyond terrestrial laboratories to astronomical observations. If axions exist, they should be produced abundantly in the cores of stars, where strong magnetic fields and high temperatures create conditions favorable for axion production. These stellar axions could potentially be detected by observing their conversion back to X-ray photons in the magnetic field surrounding neutron stars or in laboratory experiments that focus on the sunday. The CAST experiment at CERN searches for solar axions using a decommissioned LHC magnet pointed toward the sunday. If axions are produced in the solar core, some should convert to X-ray photons when they pass through CAST's magnetic field, creating a signal that varies as the magnet tracks the sun across the sky. So far, CAST has not detected solar axions, but these searches provide important constraints on axion properties that complement the dark matter searches. Axion searches also benefit from their connection to other areas of physics and astronomy. If axions compose dark matter, they could affect the cooling rates of white dwarf stars and neutron stars by providing an additional mechanism for energy loss. They might influence the dynamics of galaxy clusters, or create distinctive signatures in the cosmic microwave background radiation. These astrophysical constraints help narrow the range of axion masses and interaction strengths that need to be explored experimentally. The theoretical motivation for axions has only grown stronger as physicists have discovered additional problems that axions could solve. Beyond the strong CP problem, axions could help explain the observed asymmetry between matter and antimatter in the universe, provide a natural inflation field that drives cosmic expansion in the early universe, and offer connections to string theory and other approaches to quantum gravity. Future axion experiments will explore wider mass ranges with higher sensitivity. The planned EUCLID and MADMAX experiments will search for higher mass axions using different cavity designs and detection techniques. Space-based axion searches could take advantage of the low-noise environment and stable magnetic fields available in orbit, while improvements in quantum sensor technology continue to push the boundaries of detection sensitivity. As we contemplate these quantum mechanical searches for particles so light and elusive that they barely interact with anything, we appreciate how the search for dark matter is driving innovations in the most sensitive measurement techniques humans have ever developed. Beyond the familiar territory of WIMPs and axions lies a vast landscape of exotic dark matter candidates that challenge our imagination and stretch the boundaries of theoretical physics. from sterile neutrinos that could bridge the gap between the known and unknown sectors of particle physics to primordial black holes that might have formed in the universe's first moments. Scientists are exploring increasingly creative possibilities for what dark matter might be. These alternative candidates remind us that nature often proves to be stranger than our most conservative theories suggest. Sterile neutrinos represent one of the most intriguing possibilities in this exotic menagerie. Unlike the three types of ordinary neutrinos that participate in weak nuclear interactions, sterile neutrinos would interact with ordinary matter only through gravity, making them essentially invisible, except for their gravitational effects. Yet sterile neutrinos could mix quantum mechanically with ordinary neutrinos, occasionally converting between the two types in a ghostly dance that might be detectable in specialized experiments. The motivation for sterile neutrinos comes partly from observed anomalies in neutrino physics experiments. Several studies have reported results that don't quite fit the standard 3-neutrino model, including the LSND experiment at Los Alamos and the Mini-Booney experiment at Fermilab. These anomalies could be explained by the existence of sterile neutrinos, with masses in the keV to eV range much heavier than ordinary neutrinos, but still far lighter than typical WIMP candidates. If sterile neutrinos make up dark matter, they would have been produced in the early universe through their quantum mixing with ordinary neutrinos. This production mechanism would create warm dark matter rather than the cold dark matter typically associated with WIMPs. Warm dark matter particles retain significant velocities after decoupling from thermal equilibrium, which would suppress the formation of small-scale structures like dwarf galaxies and create subtle differences in the cosmic web compared to cold dark matter scenarios. Primordial black holes offer a radically different approach to dark matter that doesn't require any new particles beyond what we already know to exist. These black holes would have formed in the early universe from the collapse of extremely dense regions created by quantum fluctuations during cosmic inflation. Unlike stellar mass black holes that form from the collapse of massive stars, primordial black holes could have a wide range of masses depending on when they formed during cosmic history. The appeal of primordial black holes as dark matter candidates is that they would consist entirely of ordinary matter compressed to extraordinary densities, avoiding the need for exotic new physics. They would interact with ordinary matter only gravitationally, explaining why dark matter has proven so difficult to detect directly. Recent gravitational wave detections of black hole mergers by LIGO and Virgo have renewed interest in primordial black holes, particularly those with masses similar to the merging black holes observed. However, primordial black holes face significant constraints from various astronomical observations. Small primordial black holes would evaporate through Hawking radiation, creating gamma-ray backgrounds that haven't been observed. Large primordial black holes would cause gravitational lensing of distant stars that should be detectable by current surveys. Intermediate mass primordial black holes are less constrained, but they would need to account for the precise abundance of dark matter observed today. Self-interacting dark matter represents another exotic possibility that could solve some puzzles in small-scale structure formation. Standard cold dark matter simulations predict that dark matter halos should have cuspy density profiles with densities that increase steeply toward halo centers. However, observations of dwarf galaxies and low-surface brightness galaxies suggest that dark matter halos might have flatter chord density profiles, potentially indicating that dark matter particles interact with each other through forces beyond gravity. If dark matter particles can scatter off each other through some new force, these interactions could transfer energy and momentum within dark matter halos, heating their centers and creating the observed core density profiles. The strength of dark matter self-interactions must be carefully tuned. Too strong, and they would affect larger galaxies in ways that aren't observed. Too weak, and they wouldn't solve the cusp core problem. This fine-tuning requirement makes self-interacting dark matter an elegant but challenging possibility. Fuzzy dark matter, also known as ultralight dark matter, explores the possibility that dark matter consists of particles so light that their quantum mechanical wave nature becomes important on galactic scales. These particles would have masses billions of times smaller than electrons, making their de Broglie wavelengths comparable to the sizes of dwarf galaxies. This would create quantum interference effects that suppress small-scale structure formation and might explain some observed properties of dwarf galaxies. The motivation for fuzzy dark matter comes partly from string theory, which predicts the existence of ultralight scalar particles called axion-like particles. These particles would behave similarly to QCD axions, but wouldn't necessarily solve the strong CP problem. They could be produced through various mechanisms in the early universe and would create distinctive signatures in cosmic structure formation that differ from both cold and warm dark matter scenarios. Dark photons represent yet another exotic possibility, involving hidden sector particles that interact with ordinary matter through kinetic mixing with electromagnetic fields. These hypothetical particles would be massive versions of ordinary photons, mediating a new force that couples weakly to electric charge. Dark photons could comprise dark matter if they were produced through various mechanisms in the early universe, and they might be detectable through their weak electromagnetic interactions. Superfluid dark matter models propose that dark matter behaves as a quantum superfluid on galactic scales, creating collective excitations that mimic the effects of modified gravity theories. In these models, dark matter particles would condense into a superfluid state within galaxy halos, producing phonon excitations that interact with ordinary matter in ways that could explain galactic rotation curves without requiring large amounts of invisible matter. Mirror matter represents one of the most speculative dark matter candidates, involving a hidden sector of particles that are exact copies of standard model particles, but interact through mirror versions of the fundamental forces. This mirror world would be invisible to us except through gravitational interactions, but it would have its own mirror atoms, mirror stars, and potentially even mirror life. While elegant in its symmetry, mirror matter faces significant constraints from Big Bang, nucleosynthesis, and other cosmological observations. The search for exotic dark matter candidates is driving innovations in experimental techniques and theoretical modeling. New detector technologies are being developed to search for ultralight particles, while astronomical surveys are looking for the distinctive signatures that different dark matter candidates would create in cosmic structure formation. Machine learning techniques are helping astronomers identify subtle patterns in observational data that might reveal the nature of dark matter. As we contemplate this vast bestiary of exotic dark matter possibilities, we're reminded that the universe may be far stranger than our current understanding suggests. The solution to the dark matter mystery might lie in physics beyond our current theoretical frameworks. Deep beneath the Earth's surface, in caverns carved from ancient rock formations and chambers shielded by miles of stone, scientists have created some of the quietest places in the universe. These underground sanctuaries, more isolated from cosmic radiation than the surface of Mars, house experiments of extraordinary sensitivity designed to detect the faintest whispers of dark matter particles as they pass through our planet. The quest to catch WIMPs in the act of interacting with ordinary matter has driven the construction of these subterranean cathedrals of science, where every vibration is dampened, every atom purified, and every photon counted in humanity's most patient search for the invisible. The necessity of going underground for dark matter detection stems from the overwhelming background of cosmic ray particles that constantly bombard Earth's surface. Cosmic rays, high-energy protons, and atomic nuclei, accelerated by supernovae and other cosmic phenomena, create cascades of secondary particles when they hit our atmosphere. These cosmic ray showers include muons, neutrons, and other particles that can mimic the signals that dark matter particles would produce in detectors. At Earth's surface, cosmic ray muons pass through every square centimetre at a rate of about 1 per minute. For dark matter detectors, expecting perhaps one genuine signal per year, this cosmic ray background would be utterly overwhelming. Underground laboratories provide the massive shielding needed to reduce this background to manageable levels. A depth of about 2,000 meters of rock reduces the cosmic ray muon flux by a factor of about 1 million, creating the quiet environment necessary for dark matter searches. The Sanford Underground Research Facility in South Dakota, located in the former Home State gold mine, exemplifies the extreme measures taken to create these pristine research environments. At the 4,850-foot level, nearly a mile underground, The facility houses multiple dark matter experiments in caverns that were blasted from Precambrian rock formations over 1.8 billion years old. The overlying rock provides shielding, equivalent to about 4,300 meters of water, reducing cosmic ray backgrounds to levels that make dark matter detection feasible. Gran Sasso National Laboratory in Italy, built beneath the Apennine Mountains, represents another pioneering underground facility that has hosted groundbreaking dark matter experiments for decades. The laboratory's tunnels and halls are accessed through a highway tunnel that burrows through the mountain, providing both convenient access and massive shielding. Gran Sasso's unique location allows experiments to run continuously while maintaining the ultra-low background conditions essential for dark matter searches. Snow Lab in Canada, located 2,070 meters underground in an active nickel mine, has become a world-leading facility for dark matter detection experiments. The facility's ultra-clean environment requires researchers to shower and change into specially laundered clothing before entering, preventing contamination that could introduce radioactive backgrounds. Even the concrete used in Snow Lab's construction was specially formulated using low radioactivity materials to minimize backgrounds. The engineering challenges of building sensitive detectors in these underground environments are formidable. Every component must be selected for minimal radioactivity, often requiring months of screening with sensitive gamma-ray detectors to ensure acceptably low contamination levels. Copper components are often made from ancient copper recovered from Roman-era shipwrecks, because centuries underwater have allowed naturally occurring radioactive isotopes to decay to undetectable levels. Liquid xenon has emerged as the preferred target material for many WIMP detection experiments due to its favorable properties for identifying dark matter interactions. Xenon is dense enough to stop dark matter particles that might otherwise pass through lighter materials without interacting. When a WIMP or other particle scatters off a xenon nucleus, it produces both light and ionization that can be detected with extraordinary sensitivity. The X-Enon collaboration has built a series of increasingly sensitive liquid xenon detectors, culminating in the X-Enon 1T experiment and its successor, X-Enon NT. These detectors use hundreds of kilograms of liquid xenon contained in specially designed vessels surrounded by photomultiplier tubes that can detect individual photons. The ratio of light to charge signals provides a powerful tool for distinguishing potential WIMP interactions from background events caused by ordinary radioactivity. Lux Zeppelin, LZ, housed at the Sanford Underground Research Facility, represents the current pinnacle of liquid xenon dark matter detection technology. With a liquid xenon mass of about 7 tons, LZ is designed to be sensitive to WIMP interactions that are hundreds of times weaker than previous experiments could detect. The detector is surrounded by multiple layers of shielding, including a water tank that both shields against external radiation and serves as a cosmic ray veto system. The challenge of distinguishing genuine WIMP signals from background events requires sophisticated analysis techniques and multiple layers of event discrimination. Electronic recoil events caused by gamma rays and beta particles look different from nuclear recoil events that WIMPs would produce. The three-dimensional position reconstruction allows researchers to define a fiducial volume in the detector's center where backgrounds are minimized. Machine learning algorithms help identify subtle patterns that might indicate the presence of a WIMP signal. Annual modulation represents another powerful technique for WIMP detection that relies on Earth's motion through the galaxy's dark matter halo. As Earth orbits the Sun, our planet's velocity relative to the dark matter halo changes throughout the year, which should modulate the rate of WIMP interactions in a predictable way. This modulation signal would be extremely difficult for background events to mimic, providing a smoking gun signature of dark matter detection. The Dharma collaboration at Gran Sasso has claimed to observe such an annual modulation signal for over 2 decades using sodium iodide crystal detectors. However, other experiments using different detector technologies have not confirmed this result, creating one of the most contentious debates in dark matter physics. Resolving this disagreement is a major priority for the dark matter detection community. Cryogenic detectors represent another approach to WIMP detection that operates at millikelvin temperatures 1,000 times colder than outer space. These detectors can measure both the phonons, crystal vibrations, and ionization produced. When particles interact with the target material, the CDMS, Super CDMS, and CREST experiments use this technology to achieve excellent background discrimination and sensitivity to low-mass WIMPs. Directional detection experiments attempt to measure not just the energy of WIMP interactions but also the direction from which the WIMPs arrive. Since Earth is moving through the galaxy's dark matter halo, WIMPs should appear to come preferentially from the direction of Earth's motion. Directional detectors use low-pressure gas chambers, where nuclear recoils create tracks that can be measured with extraordinary precision. As these underground sentinels continue their patient vigil, pushing the boundaries of sensitivity ever deeper into unexplored parameter space, they represent humanity's most sophisticated attempt to make contact with the invisible realm that dominates our universe. High above the rolling countryside near Geneva, Switzerland, protons race through a 27-kilometer circular tunnel at nearly the speed of light, carrying energies that briefly recreate conditions from a trillionth of a second after the Big Bang. The Large Hadron Collider represents humanity's most powerful tool for probing the fundamental structure of matter and energy, and it might also be our most promising method for producing dark matter particles in controlled laboratory conditions. Through the violent collision of these accelerated protons, physicists hope to create dark matter particles that would immediately escape detection, revealing their presence only through the energy and momentum they carry away invisibly. The strategy of producing dark matter at particle accelerators complements the direct detection experiments buried deep underground. While underground detectors wait patiently for dark matter particles from space to interact with terrestrial matter, the accelerator experiments take the offensive approach of creating dark matter particles and studying their properties directly. This complementarity is crucial because the two approaches probe different aspects of dark matter physics and can together provide a complete picture of dark matter's properties. If dark matter consists of WIMPs or other particles that were in thermal equilibrium in the early universe, then high-energy collisions at the LHC should be able to produce pairs of these particles through the same processes that created them after the Big Bang. The collision energies available at the LHC, up to 14 trillion electron volts, are sufficient to produce particles with masses up to several times the mass of a proton, covering much of the theoretically preferred range for WIMP masses. The signature of dark matter production at particle accelerators is missing energy and momentum. When two protons collide at the LHC, conservation laws require that the total energy and momentum before the collision equal the total energy and momentum after the collision. If dark matter particles are produced in the collision, they will escape the detector without leaving any trace, creating an imbalance in the measured energy and momentum that reveals their presence. This missing energy signature is challenging to detect because many ordinary processes can also create apparently missing energy. Neutrinos, which interact so weakly that they escape all particle detectors, create genuine missing energy that must be distinguished from potential dark matter signals. Detector malfunctions, measurement errors, and poorly reconstructed particles can all mimic missing energy signatures, requiring sophisticated analysis techniques to identify genuine signals. The ATLAS and CMS experiments at the LHC have conducted extensive searches for dark matter production, looking for events where energetic jets of particles are produced in association with large amounts of missing energy. These monojet searches assume that dark matter particles are produced together with a high-energy quark or gluon that creates a visible jet, providing a trigger for the experiment's data acquisition system. The missing energy associated with dark matter production would then show up as an imbalance in the event's total momentum. Supersymmetric models provide specific predictions for dark matter production at the LHC. If the lightest supersymmetric particle is stable and neutral, it would be an ideal dark matter candidate that should be produced in the decays of heavier supersymmetric particles. The LHC experiments have searched extensively for these supersymmetric signatures, looking for events with multiple jets, missing energy, and sometimes leptons that would indicate the production and decay of supersymmetric particles. Despite years of searching, neither ATLAS nor CMS has found convincing evidence for dark matter production or supersymmetric particle production. These null results have placed increasingly stringent constraints on the masses and interaction strengths of potential dark matter particles. The absence of signals at the LHC has forced theorists to consider models where dark matter interacts even more weakly with ordinary matter than originally anticipated. The high luminosity LHC, which will begin operations in the late 2020s, will provide significantly more collision data than the current LHC, increasing the sensitivity to rare dark matter production processes. This upgraded collider will be capable of producing about 10 times more collisions per year, allowing searches for extremely rare processes that might have escaped detection in earlier runs. The increased dataset will also enable more sophisticated analysis techniques that could reveal subtle signals hidden in the noise of ordinary collisions. Future colliders beyond the LHC will extend the search for dark matter production to even higher energies and with greater precision. The proposed future circular collider would have a circumference of 100 kilometers and collision energies up to 100 trillion electron volts, 7 times higher than the LHC. This enormous energy reach would enable the production of dark matter particles with masses up to tens of times the proton mass, exploring previously inaccessible regions of theoretical parameter space. Lepton colliders, which accelerate electrons and positrons rather than protons, offer complementary advantages for dark matter searches. Because leptons are fundamental particles, rather than composite objects like protons, lepton collisions are much cleaner and easier to interpret theoretically. The proposed International Linear Collider and Compact Linear Collider would be capable of precise measurements that could reveal subtle effects of dark matter interactions. The connection between particle accelerator searches and cosmic dark matter depends critically on the assumption that dark matter particles can be produced in high-energy collisions. This assumption is reasonable if dark matter consists of particles that were in thermal equilibrium in the early universe, but it might not apply to other dark matter candidates like axions or sterile neutrinos that were produced through non-thermal mechanisms. Accelerator searches for dark matter have also stimulated the development of new theoretical frameworks that connect particle physics to cosmology. These studies have revealed the importance of considering the full context of early universe physics when interpreting accelerator results. The properties of dark matter particles that can be probed at accelerators might differ significantly from the properties that are relevant for cosmic structure formation. The collaboration between accelerator physicists and cosmologists has led to new insights about the relationship between microscopic particle properties and macroscopic cosmic phenomena. This interdisciplinary approach has become essential for understanding how discoveries at particle accelerators relate to observations of cosmic structure and dark matter's role in galaxy formation. Machine learning and artificial intelligence techniques are revolutionizing how physicists search for dark matter signals in accelerator data. Neural networks can identify complex patterns in collision data that might indicate the presence of dark matter production, while deep learning algorithms can distinguish potential signals from background processes with unprecedented accuracy. As particle accelerators push toward higher energies and greater precision, they continue to serve as time machines that recreate the conditions of the early universe, potentially producing the very particles that shape cosmic evolution today. In the summer of 1983, an Israeli physicist named Mordechai Milgram published a paper that would fundamentally challenge the dark matter paradigm by proposing a radical alternative. Perhaps the problem isn't missing matter, but rather our incomplete understanding of gravity itself. Milgram's modified Newtonian dynamics, known as MOND, suggested that Newton's laws of motion break down at the extremely low accelerations present in the outer regions of galaxies, naturally explaining galactic rotation curves without requiring any invisible matter. This elegant proposal has sparked decades of debate about whether dark matter exists or whether we need to modify our most fundamental theories of space, time, and gravitation. MOND emerged from Milgram's careful analysis of galactic rotation curves and his recognition that the missing mass problem appeared at a characteristic acceleration scale. When he examined Vera Rubin's data and similar observations from other astronomers, Milgram noticed that the deviation from Newtonian predictions always occurred when the gravitational acceleration fell below a critical value of about -10 meters per second, squared roughly 100 billion times. weaker than Earth's surface gravity. This critical acceleration scale, which Milgram denoted as 0, represents the boundary between the regime where Newton's laws work perfectly and the regime where they begin to fail. Above this acceleration, stellar orbits, planetary motion, and laboratory experiments all follow Newton's laws with extraordinary precision. Below this acceleration, in the outer regions of galaxies where dark matter effects become apparent, Mond proposes that the gravitational force becomes stronger than Newton's law predicts. The mathematical formulation of Mond modifies Newton's second law, F equals ma, by introducing a function that changes the relationship between force and acceleration when accelerations become very small. In the high acceleration limit, this function reduces to Newton's familiar law, preserving all the successes of Newtonian mechanics in the solar system and laboratory experiments. In the low acceleration limit, the modification causes gravitational effects to fall off more slowly with distance, mimicking the effects attributed to dark matter. The remarkable aspect of Mond is its ability to predict galactic rotation curves with only a single new parameter, the critical acceleration as 0. Once this parameter is fixed from observations of one galaxy, Mond makes parameter-free predictions for the rotation curves of all other galaxies. These predictions have proven to be extraordinarily successful, matching observed rotation curves with an accuracy that rivals or exceeds dark matter models. Mond's success extends beyond simple spiral galaxies to more complex systems. The theory correctly predicts the rotation curves of elliptical galaxies, the velocity dispersions of gas and stars in irregular galaxies, and even the internal dynamics of globular clusters. Perhaps most remarkably, Mond predicts a tight correlation between the visible matter in galaxies and their observed rotation velocities, a relationship that emerges naturally from the theory but requires fine-tuning in dark matter models. The Tully-Fisher relation, which links galaxy luminosity to rotation velocity, finds a natural explanation in Mond. This empirical relationship, observed across many decades of galaxy luminosity, emerges automatically from Mond's modified dynamics without requiring any assumption about dark matter halo properties. In contrast, dark matter models struggle to explain why this relationship should be so tight and universal across different galaxy types and cosmic epochs. However, Mond faces significant challenges when extended beyond individual galaxies to larger cosmic structures. Galaxy clusters, which provided the first evidence for dark matter through Fritz Zwicky's observations, remain problematic for Mond. Even with the enhanced gravitational effects that Mond provides, most clusters still require substantial amounts of additional matter to explain the high velocities of their member galaxies and the temperature of their hot gas. The Bullet cluster presents a particularly severe challenge for Mond and other modified gravity theories. The spatial separation between the bulk of normal matter and the gravitational mass, as revealed by gravitational lensing, is difficult to explain without invoking dark matter as a separate component. While Mond proponents have proposed various mechanisms to address this problem, none have achieved the elegant simplicity that characterizes Mond's explanation of galactic dynamics. Relativistic extensions of Mond have been developed to address cosmological observations and provide a complete alternative to the dark matter paradigm. Jacob Bekenstein's tensor vector, scalar, Tevez theory represents the most successful attempt to embed Mond's dynamics within a relativistic framework compatible with general relativity's successes. Tevez introduces additional fields beyond the metric tensor of general relativity, allowing the theory to reproduce Mond's predictions in the appropriate limits. Recent developments in modified gravity have explored connections to fundamental physics and quantum gravity. Eric Verlinde's emergent gravity proposals suggest that gravitational forces might emerge from the entanglement structure of spacetime itself, naturally producing Mond-like modifications at low accelerations. These approaches attempt to derive modified gravity from more fundamental principles rather than simply postulating new dynamics. The observational tests that could distinguish between dark matter and modified gravity continue to evolve as new data becomes available. Wide binary star systems in our galaxy provide a clean test of Mond predictions, because these systems have accelerations near the critical scale as 0 but are free from the complications of dark matter halos. Recent observations suggest that wide binaries might indeed show deviations from Newtonian dynamics consistent with MOND predictions. Gravitational wave astronomy offers new opportunities to test modified gravity theories. The recent detections of gravitational waves from merging black holes and neutron stars have confirmed that gravitational waves propagate at the speed of light, constraining many modified gravity theories. Future gravitational wave observations might detect more subtle effects that could distinguish between dark matter and modified gravity explanations for cosmic structure. The cosmic microwave background provides another crucial test for modified gravity theories. The observed patterns of temperature fluctuations encode information about the universe's composition and evolution during its first few 100,000 years. While MOND successfully explains galactic dynamics, extending it to cosmological scales requires additional assumptions that may be inconsistent with cosmic microwave background observations. Machine learning techniques are being applied to test modified gravity theories against observational data. Neural networks can analyze complex datasets to identify signatures that might distinguish between dark matter and modified gravity predictions. These computational approaches are particularly valuable for comparing theories across multiple observational probes simultaneously. The philosophical implications of the dark matter versus modified gravity debate extend beyond technical physics to questions about the nature of scientific explanation and the role of simplicity in theory choice. MOND offers a remarkably simple explanation for galactic dynamics, but requires additional complexity to address cosmological observations. Dark matter provides a unified framework for understanding cosmic structure, but requires postulating the existence of an entirely new component of reality. As we contemplate these competing visions of cosmic architecture, one dominated by invisible matter and another governed by modified gravitational dynamics, we're reminded that science often progresses through the tension between radically different explanations for the same phenomena. In the cosmic dance of structure formation that has unfolded over 13.8 billion years, dark matter has served as both choreographer and stage, providing the gravitational framework within which galaxies condensed from the primordial cosmos and evolved into the magnificent spiral and elliptical systems we observe today. Without dark matter's invisible scaffolding, the universe would be a featureless expanse of cooling gas, devoid of the stellar cities that light up the cosmic night. Understanding how galaxies form within dark matter halos has become one of the most active frontiers in astrophysics, revealing how the seen and unseen components of the cosmos have collaborated to create cosmic complexity. The story of galaxy formation begins in the early universe, when dark matter started clumping together under its own gravity, while ordinary matter remained smooth and uniform. This head start was crucial because ordinary matter was coupled to radiation through electromagnetic interactions, preventing it from forming dense concentrations until the universe had cooled sufficiently for atoms to form. Dark matter, immune to radiation pressure, could begin the slow process of gravitational collapse as soon as cosmic expansion had diluted the universe enough for gravity to overcome the initial expansion velocity. Computer simulations reveal that dark matter halos form through a hierarchical process, with small halos merging to form larger ones in a cosmic game of gravitational accumulation that continues throughout cosmic history. The first dark matter halos formed when the universe was only a few 100 million years old and had masses comparable to large asteroids. Through endless mergers and accretion, these tiny seeds grew into the massive halos that today contain galaxy clusters, some with masses exceeding 1 billion times the mass of our Sunday. The relationship between dark matter halos and the galaxies they host follows patterns that reveal deep connections between visible and invisible cosmic components. More massive dark matter halos tend to contain more luminous galaxies with greater stellar masses, but this relationship is not simple or linear. The efficiency of converting gas into stars depends on halo mass in complex ways, with the most efficient star formation occurring in halos with masses similar to that of the Milky Way, about 1 trillion times the mass of the Sunday. Very massive dark matter halos, those exceeding 10-13 solar masses, tend to host elliptical galaxies, where star formation has largely ceased. The enormous gravitational potential wells of these massive halos heat in falling gas to such high temperatures that it cannot cool efficiently and condense into stars. Instead, this hot gas creates the X-ray emitting atmospheres that surround massive elliptical galaxies and galaxy clusters, representing a fossil record of failed star formation. At the opposite extreme, very small dark matter halos struggle to retain gas and form stars efficiently. Stellar feedback processes, supernova explosions, stellar winds, and radiation pressure from young stars can drive gas out of small halos more easily than from massive ones. This explains why many small dark matter halos remain essentially invisible, containing little or no stellar material, despite having sufficient mass to gravitationally bind a small galaxy. The cuspy halo problem represents one of the most persistent challenges in understanding dark matter's role in galaxy formation. Computer simulations consistently predict that dark matter halos should have cuspy density profiles, with densities that increase steeply toward the halo center. However, observations of dwarf galaxies and low-surface brightness galaxies suggest that their dark matter halos have flatter, chord density profiles, with constant densities near their centers. Various solutions to the cuspy halo problem have been proposed, most involving feedback processes that transfer energy from stars to dark matter. Supernova explosions and other stellar feedback mechanisms could create oscillations in the gravitational potential that gradually heat dark matter and reduce central densities. Alternatively, the problem might indicate that dark matter has weak self-interactions that allow energy transfer between dark matter particles themselves. The missing satellites problem poses another puzzle for dark matter-based galaxy formation models. Simulations predict that massive halos, like the Milky Way's, should contain hundreds of smaller subhalos that could potentially host dwarf satellite galaxies. However, the Milky Way has only about 50 known satellite galaxies, and most of these are much fainter than simulations predict. This discrepancy might indicate that most small halos remain dark due to stellar feedback, or it could point to more fundamental problems with dark matter models. Galaxy formation within dark matter halos involves complex feedback loops between stellar processes and the surrounding dark matter and gas. When massive stars explode as supernovae, they inject energy and momentum into the surrounding medium, driving outflows that can remove gas from the galaxy entirely. These outflows affect not just the gas content, but also the distribution of dark matter by changing the gravitational potential of the galaxy. The role of supermassive black holes in galaxy formation adds another layer of complexity to the interplay between dark matter and visible matter. Most galaxies contain central black holes with masses that correlate remarkably well with the velocity dispersions of their stellar bulges. This correlation suggests a fundamental connection between black hole growth and galaxy formation that might be mediated by the properties of dark matter halos. Active galactic nuclei, galaxies with actively accreting supermassive black holes, can produce powerful jets and winds that affect galaxy evolution on scales much larger than the galaxies themselves. These feedback processes can heat gas throughout entire dark matter halos, suppressing star formation and altering the relationship between halo mass and galaxy properties. Understanding this AGN feedback has become crucial for explaining why the most massive galaxies stopped forming stars billions of years ago. The cosmic web of dark matter filaments plays a crucial role in supplying galaxies with the gas needed for continued star formation. Galaxies grow by accreting gas that flows along dark matter filaments, and the rate of this accretion depends on both the halo mass and the local environment. Galaxies in dense clusters typically have their gas supply cut off as they fall into the cluster, while isolated galaxies can continue accreting gas and forming stars for much longer periods. Modern galaxy formation models incorporate increasingly sophisticated treatments of the complex physics involved in transforming gas into stars within dark matter halos. These models must account for molecular cloud formation, stellar initial mass functions, stellar feedback, chemical enrichment, magnetic fields, and cosmic ray transport, all operating within the gravitational framework provided by dark matter. Machine learning techniques are revolutionizing how astronomers compare galaxy formation models with observations. Neural networks can identify subtle correlations between galaxy properties and their dark matter environments that would be impossible to detect through traditional analysis methods. These approaches are revealing new connections between visible and invisible cosmic components. As we contemplate the intricate choreography of galaxy formation, we gain deep appreciation for how dark matter provides the stable, gravitational stage upon which the drama of cosmic evolution unfolds. Between the moment when the cosmic microwave background was released and the ignition of the first stars lies one of the most mysterious epochs in cosmic history, the cosmic dark ages, a period when the universe contained no sources of light and existed in complete darkness. During this interval, spanning hundreds of millions of years, dark matter was quietly working behind the scenes, gathering into ever larger concentrations that would eventually provide the gravitational wells necessary for the first stars to form. Understanding this hidden epoch has become crucial for comprehending how the universe transitioned from primordial simplicity to the rich complexity we observe today. The cosmic dark ages began about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. This recombination event marked the end of the universe's opaque phase and released the cosmic microwave background radiation that we observe today. But once these photons escaped, the universe entered a period of darkness that would last for hundreds of millions of years, illuminated only by the fading afterglow of the Big Bang itself. During this dark epoch, the universe consisted primarily of neutral hydrogen and helium gas, cooling through adiabatic expansion, with no sources of light except the gradually redshifting cosmic microwave background. The temperature dropped from thousands of degrees at recombination to mere tens of degrees by the end of the Dark Ages, creating conditions cold enough for molecular hydrogen to form the crucial molecule that would eventually enable the first stars to ignite through gravitational collapse. Dark matter played the starring role during the cosmic Dark Ages, even though it remained completely invisible. Free from the radiation pressure that had prevented ordinary matter from clumping during the earlier epochs, dark matter continued the gravitational collapse that had begun shortly after cosmic inflation. Small dark matter halos merged to form larger ones in a hierarchical process that gradually built up the cosmic web of structure that spans the universe today. The first dark matter halos to form were much smaller than those that host galaxies today, with masses perhaps 1,000,000 times smaller than the Sunday. These mini-halos were the fundamental building blocks of cosmic structure, serving as the sites where ordinary matter would first collect in significant concentrations. Computer simulations show that these early halos had very different properties from the massive halos we observe today, with much higher central densities and more compact structures. As dark matter halos grew through mergers and accretion, they began to attract ordinary matter through their gravitational influence. Gas flows along dark matter filaments created streams of matter that fed the growing halos, gradually building up reservoirs of hydrogen and helium that would eventually provide the raw material for star formation. This process of gas accretion was slow and gentle compared to later epochs, allowing time for the complex chemistry needed to form molecular hydrogen. The formation of molecular hydrogen represents one of the most important developments during the cosmic dark ages. Unlike atomic hydrogen, molecular hydrogen can cool efficiently through rotational and vibrational transitions, allowing gas clouds to reach the low temperatures necessary for gravitational collapse. Without molecular hydrogen, gas clouds would remain too hot to overcome their internal pressure and collapse into stars, potentially leaving the universe dark forever. The chemistry of molecular hydrogen formation in the early universe was completely different from what we observe today. In the absence of heavy elements and dust grains, which had not yet been produced by stellar nucleosynthesis, hydrogen molecules had to form through much less efficient gas phase reactions involving hydrogen, anions, and other exotic species. This inefficient chemistry meant that only tiny fractions of the available hydrogen could be converted into molecular form. Dark matter's gravitational influence was crucial for concentrating gas to the densities where molecular hydrogen chemistry could operate effectively. In the smooth, low-density universe that existed after recombination, the formation of molecular hydrogen would have been impossibly slow. But within dark matter halos, where gas densities were enhanced by factors of hundreds or thousands, molecular hydrogen could form in quantities sufficient to enable cooling and collapse. The end of the cosmic dark ages came with the ignition of the first stars, an event that cosmologists call cosmic dawn. These first stars formed within the most massive dark matter halos, available at the time structures with masses perhaps 100 million times that of the Sunday. The stars themselves were very different from modern stars, lacking any elements heavier than lithium and therefore having very different properties from the metal-enriched stars we observe today. The first stars were likely much more massive than typical stars today, possibly ranging from tens to hundreds of times the mass of the Sun. These massive stars burned through their nuclear fuel rapidly and exploded as supernovae after just a few million years, dispersing the first heavy elements into the surrounding gas. These elements, carbon, oxygen, nitrogen, and others, would play crucial roles in the chemistry of subsequent star formation. The transition from the cosmic dark ages to the epoch of first light represents one of the most dramatic phase transitions in cosmic history. The universe went from being completely dark to containing sources of light that would begin the process of reionizing the neutral hydrogen that pervaded all of space. This reionization epoch would last for several hundred million years, during which ultraviolet radiation from stars and early galaxies gradually ionized most of the hydrogen in the universe. Observations of the cosmic dark ages remain challenging because this epoch occurred before any sources of electromagnetic radiation existed. However, radio astronomy offers a promising way to study this period through observations of the 21-centimeter line of neutral hydrogen. This radiation is emitted when the electron in a hydrogen atom flips its spin relative to the proton, creating a radio signal that can potentially be detected by sensitive radio telescopes. The 21-centimeter signal from the cosmic dark ages would carry information about the density and temperature of neutral hydrogen throughout this epoch, potentially revealing details about how dark matter halos grew and how gas accumulated within them. Detecting this signal requires distinguishing it from much brighter foreground sources, including our own galaxy and radio galaxies at various distances. Future radio telescope arrays, like the Square Kilometre Array, SKA, and the Hydrogen Epoch of Reionization Array, HERA, are being designed specifically to detect 21-centimeter radiation from the cosmic dark ages and the epoch of reionization. These observations could provide the first direct view of how dark matter shaped cosmic evolution during the universe's first billion years. As we contemplate this vast epoch of cosmic darkness, when dark matter was patiently assembling the gravitational framework for all subsequent cosmic evolution, we gain appreciation for how invisible processes occurring over hundreds of millions of years set the stage for the magnificent universe of light and structure that surrounds us today. In the dense cores of dark matter halos throughout the universe, a ghostly process might be occurring that could provide our first direct glimpse into dark matter's true nature. If dark matter consists of particles that can annihilate with their antiparticles, these cosmic collisions would produce high-energy photons, neutrinos, and other detectable particles that travel across the galaxy to reach our instruments. The search for these annihilation signals has opened an entirely new approach to dark matter detection, one that looks not for dark matter particles themselves, but for the energetic aftermath of their mutual destruction. The theoretical foundation for dark matter annihilation comes from particle physics models where dark matter particles have antiparticle partners. In these scenarios, when a dark matter particle encounters its antiparticle, they annihilate in a burst of energy that converts their combined mass into lighter particles, according to Einstein's famous equation, E equals mc squared. This process would be the reverse of the mechanism that created dark matter in the early universe, when high-energy collisions produced particle-antiparticle pairs that survived as relic dark matter after the universe cooled. The rate of dark matter annihilation depends critically on the density of dark matter and the probability that particles will interact when they encounter each other. This makes the centers of galaxies and galaxy clusters particularly promising targets for annihilation searches, since these regions contain the highest concentrations of dark matter in the universe. The galactic center of the Milky Way, located about 26,000 light-years away in the direction of the constellation Sagittarius, represents perhaps the most promising target for detecting dark matter annihilation signals. Gamma-ray astronomy has emerged as the primary tool for searching for dark matter annihilation, since high-energy photons can travel across the galaxy without being absorbed or scattered by intervening matter. The Fermi Gamma-ray Space Telescope, launched in 2008, has conducted systematic surveys of the gamma-ray sky with unprecedented sensitivity, mapping the diffuse gamma-ray emission from various astrophysical sources while searching for the distinctive signatures that dark matter annihilation would produce. The challenge of identifying dark matter annihilation signals lies in distinguishing them from the numerous astrophysical sources that also produce gamma rays. The galactic center region contains a supermassive black hole, stellar remnants, cosmic ray interactions, and other energetic phenomena that create a complex background of gamma ray emission. Separating potential dark matter signals from this astrophysical background requires careful modeling of known sources and sophisticated statistical analysis techniques. One of the most intriguing discoveries from the Fermi telescope has been the detection of a diffuse excess of gamma rays emanating from the inner regions of the Milky Way. This galactic center excess has the right energy spectrum and spatial distribution to be consistent with dark matter annihilation, though alternative explanations involving millisecond pulsars or other astrophysical sources remain viable. The debate over the origin of this signal has driven improvements in both theoretical modeling and observational techniques. The expected spectrum of gamma rays from dark matter annihilation depends on the mass of the dark matter particles and the specific channels through which they annihilate. Heavy dark matter particles would produce higher energy gamma rays, while lighter particles would create lower energy photons. The relative intensities at different energies could reveal information about the fundamental physics governing dark matter interactions. Dwarf, spheroidal galaxies represent another promising class of targets for dark matter annihilation searches. These small satellite galaxies of the Milky Way are thought to be dominated by dark matter, with very little ordinary matter to create confusing astrophysical backgrounds. The lack of active star formation or other energetic processes in these systems makes them ideal laboratories for detecting pure dark matter annihilation signals. Observations of dwarf galaxies with the Fermi telescope and ground-based atmospheric Cherenkov telescopes have placed increasingly stringent limits on dark matter annihilation rates. While no definitive signals have been detected, these observations have ruled out many theoretical models for dark matter particles and have begun to probe the parameter space where dark matter annihilation should be detectable, if it occurs at the rates predicted by thermal relic models. Neutrino astronomy offers another avenue for detecting dark matter annihilation, particularly for dark matter particles that preferentially annihilate into neutrinos rather than photons. The IceCube Neutrino Observatory, buried in the Antarctic ice, has searched for neutrino signals from dark matter annihilation in the galactic center, the Sun, and the Earth. While no clear signals have been detected, these searches provide complementary constraints on dark matter properties. The search for dark matter annihilation in the Sun represents a particularly sensitive probe because dark matter particles from the galactic halo can become gravitationally trapped in the solar core, where they accumulate over billions of years and reach very high densities. If these trapped particles annihilate, they would produce neutrinos that could escape the Sun and be detected by neutrino telescopes on Earth. The absence of such signals places strict limits on the rate at which dark matter particles interact with ordinary matter. Antimatter searches provide yet another approach to detecting dark matter annihilation. When dark matter particles annihilate, they can produce antiparticles like positrons and antiprotons that travel through the galaxy before being detected by space-based instruments. The Alpha Magnetic Spectrometer, AMS-02, on the International Space Station has measured the cosmic ray positron fraction with unprecedented precision, revealing an excess of positrons at high energies that could potentially be explained by dark matter annihilation. However, astrophysical sources like pulsars can also produce positron excesses, making it difficult to definitively attribute the observed signals to dark matter. The energy spectrum and spatial distribution of cosmic ray antimatter provide clues about their origin, but disentangling dark matter signals from astrophysical backgrounds remains a major challenge in antimatter-based dark matter searches. Indirect detection experiments face the fundamental challenge that dark matter annihilation signals must be distinguished from astrophysical backgrounds that can mimic dark matter signatures. Machine learning techniques are increasingly being used to analyze complex datasets and identify subtle patterns that might indicate dark matter annihilation. Neural networks can process multi-wavelength observations simultaneously, potentially revealing correlations that traditional analysis methods might miss. The theoretical framework for dark matter annihilation continues to evolve as particle physicists explore new models for dark matter interactions. Some theories propose that dark matter undergoes secluded annihilation, where dark matter particles first annihilate into intermediate particles that then decay into standard model particles. This multi-step process could explain why direct annihilation signals haven't been detected while still allowing for observable, indirect signatures. Sommerfeld enhancement represents another theoretical mechanism that could boost dark matter annihilation rates in dense environments. This quantum mechanical effect occurs when dark matter particles interact through long-range forces, causing their wave functions to be focused and increasing the probability of annihilation. Sommerfeld enhancement could make annihilation signals much brighter in galaxy centers and other high-density regions. The connection between dark matter annihilation and cosmic ray physics has revealed new insights about how energetic particles propagate through the galaxy. Understanding the diffusion of cosmic rays through magnetic fields, their interactions with interstellar gas and radiation, and their acceleration by shockwaves has become crucial for interpreting potential dark matter signals. These studies have advanced our understanding of galactic astrophysics while improving dark matter search strategies. Future gamma-ray observatories will extend the search for dark matter annihilation to higher energies and with greater sensitivity. The Cherenkov Telescope Array, CTA, currently under construction, will be the world's largest ground-based gamma-ray observatory, capable of detecting gamma rays with energies up to 100 trillion electron volts. This energy range is particularly promising for detecting heavy dark matter particles that would produce very high-energy annihilation products. As we contemplate these cosmic particle collisions that might be occurring throughout the dark matter halos that surround us, we're reminded that the invisible universe might be far more dynamic and energetic than its ghostly nature initially suggests.